The cryptography class. I'm just checking to make sure it's on Monday. It is. Okay, good, because I do get confused easily. Oh, by the way, I heard today that apparently the teachers here might go on strike. So if that happens, I'll let you know.
I thought they did last week. I saw somebody breaking up.
Yeah, I heard that some people were marked, but apparently they weren't on strike. Anyway, I've heard rumors that they haven't really had a strike yet, but they might. If they do, I'll put a note on my website and let you know.
They only had the protest.
Yeah, they had a protest, and they've had a strike authorization vote, but they haven't called for a strike yet, but they presumably will pretty soon. So I'll try and let you guys know if this means I have to cancel some classes, which I imagine it will. I don't think I'll cross the picket line, although I think the union is doing pretty bad things. I do think the teachers here have pretty legitimate grievances, and I'm not going to be a scab and cross the picket line. They're correct that they need better treatment from the management, although I think they're focusing on the wrong thing. What's
they naming the team?
The team?
They naming the team. The team.
The dean?
Yeah, they complain about the dean.
Well, yeah, you can complain about all the management. The dean you can complain about too. There's a lot of people in management you can complain about. In general, they're right to complain about the management here. Anyway, so let's take a look at hard problems. So I'll put a note on my website if I have to cancel class because of a strike. All right, so we're going to talk about what hardness is, and then the problems that are important for cryptography, factoring discrete logarithm. So computational hardness is an important concept, but it is a vague concept. What it is you decide how difficult a problem is compared to other problems. You can sort them into categories. And the point is there are certain problems that are extremely difficult, so you'll never be able to do them no matter how much hardware or processor time you have. And what you do is you measure the order of complexity. Typically, in time is the most important thing. So if you consider this, suppose I want to search through n unordered elements to find something, like a shuffled deck of cards, and I'm going to go in there and find one card. Well, there's n items, so if I just hunt through them one by one looking for it, you expect to find the right one about halfway through. And so the expected amount of time it will take is n over 2 steps. That's complexity is linear in n. If I double the size of the array, I will double the time it takes to find them. So that's one order of n. Now, if I search a list, that's linear or order of n. If I sort a list, the fastest way to sort a list is to sort it into categories, like 4 categories, and then sort each of those small categories again, and that way the number of passes is the logarithm of n. That's n log n. You have to go through the whole list this many times. For example, if it's a binary number, you sort by 1 bit, then you sort by the next bit and the next bit, and you have to pass through the whole list as many times as there are bits. So that's n log n. Brute force key recovery. If you consider like AES, you have 128 bits, and if you have to decrypt something without knowing the key, you have to do 2 to the 128 calculations, so that's exponential in the number of bits in the key, 2 to the n. And quadratic time is things might be n squared. Well, they're searching through a square area for something. So you can rate how fast these are. You just rate how fast these things grow as you increase n. Here's linear, where you go up to 25, and it's going to be up to maybe 25 or 50 here, 2n. The quadratic will grow as the square of n, and exponential will grow much faster. And so it turns out that even quadratic is not all that fast, but exponential is really, really fast. So if you start considering big changes like 10, 1,000, 100, 1,000,000, you very rapidly reach unthinkable numbers that you can never actually accomplish. And that's the point. So polynomial time is n squared, n cubed, n fourth, n to the anything. Those are all considered practically feasible, even n to the fourth and n to the fifth that grow pretty fast. That's what's considered slow growth. What's fast is like 2 to the n or n to the log n. Those grow much faster so that it just reaches an astronomical number of calculations you can never do. So that's, and here's quadratic, and here's n to the log n, and here's 2 to the n. And both of them, you see, they get really steep, they grow really fast. And so they are really much more difficult than any polynomial. So there you define the complexity classes. You can, by the way, do the same thing. Well, this is in time, right? So time of n squared is all problems solved in order of n squared. Time of 2 to the n is all problems solvable in 2 to the n time steps. And you can also determine the space it takes, by the way. You could have a problems that are memory hard instead of time hard, where it takes a certain amount of memory, although I don't know very many of them except a couple of blockchain things designed specifically for that reason. All right, so the main thing you talk about is time, although you could, in principle, the same thing would apply to memory. So P is the class of all polynomial time algorithms, and NP is the class of non-deterministic polynomial time algorithms. And what these are is problems where you can verify a solution in polynomial time, but it might be hard to find. So P is a subset of NP. And this is the famous thing you hear in all computer science circles for decades. Does P equal NP or not? P are the easy problems, and NP are the hard problems in vague terms. And we're going to talk in more detail about how this works. So here's an NP problem. Recovering a secret key with the known plaintext. Well, that's easy to verify whether the key is correct. You use the key and you can tell if it worked or not, if the plaintext becomes readable. So using a secret key is an easy problem. Finding the key is a hard problem. So if you want to consider, now problems that are outside NP and P, these are not all problems are in either of these groups. For example, if you try to brute force the one-time pad, you have a series of letters, and there's a pad that you don't know where each letter is transmitted differently. Well, if you brute force that, you will create all possible series of letters, many of which will be readable, and you don't know which one is right. So even if you have all the computers in the world and all the time in the world, you'll never get in. It's infinitely hard. You can't say it's the order of 2 to the n or n to the n or anything. And here's another one. If you have a problem and you wonder if there's a solution, you want to prove that there is no solution, there is no way to ever do that. You have to try all possible solutions. There are an infinite number of possible solutions. So this is another problem you can state, but you cannot solve it with either NP or P. So that's the thing to know. There are these things called NP complete problems, and they are the hardest problems in NP, and we don't know how to solve them in polynomial time, but we have proven that they're all equally hard. And if you ever find a way to solve any one of these problems, you could solve them all. And these are several famous problems, like the traveling salesman problem. You've heard of this. If you have to visit certain cities on a map, and you try to find the order in which to visit them till you make the shortest route, that turns out to be a very difficult problem and to grow very rapidly with the number of cities to where it is essentially unsolvable. And the clique problem is another one, where if you have a series of nodes connected by edges, you want to find the largest clique, which is a group of them where every one of them is directly connected to another. So here you have a group of 4 that are fully connected, and that's the largest one. But if you grow the grid, finding the largest clique is another problem, like the traveling salesman problem, that becomes very, very complicated. Because, again, just like the traveling salesman problem, you have to consider all combinations of these. That's the problem. In the traveling salesman problem, if you have 10 routes, you have to consider all possible ways to go through it. And if you have 100, there's many, many more ways to go through it. And it's the same problem here. And another similar one is here, the knapsack problem. If you have a set of items, and you can only fit a certain amount of total weight in your knapsack, and a total amount of value. So the question is, if you have items of known value and weight, how can you pick a group of items so that they do not exceed the allowed weight, but they have the maximum total value? And that also is again, the same thing. The problem is that you have to consider all possible combinations of the items, and that turns out to be a very large number. And so, now, by the way, some video games are NP complete, it turns out. Tetris, Super Mario Brothers, Candy Crush, Saba, and some are perhaps even NP hard. And so this is the big question. Does P equal NP? If you could solve the hardest NP problem in polynomial time, then you could solve them all in polynomial time, and then NP would equal P. And this is sort of the fundamental question. Is there anything that is really hard in mathematics? There are some problems that we currently regard as hard, like solving an AES encryption without knowing the key, but do you really know that is impossible? And we don't know that. Factor prime numbers, that's the issue. There's $1 million bounty for the proof if anybody can prove that P equals NP. No one has proven whether this is true or not yet mathematically, but it is greatly believed by almost everybody involved that P does not equal NP, that hard problems are really hard, even though we can't prove that yet. It is possible that all the problems we think are hard have a simple solution that would make them easy, and we just haven't found it yet. So here's how it is. You have P down here, the easy problems. You have NP here, which is the class of all problems that can be verified in polynomial time, which includes P. Then you have the NP complete problems down here, which are, I think, not the hardest, but the NP complete are the hardest problems in NP. And then you have problems we use for cryptography, like factoring, are over here. They're in NP, but they're not the hardest ones in NP. And so, anyway, does P equal NP? Most people say no. If it did, then in principle, all these problems would be easy and no cryptography would be secure. You'd be able to undo anything. So philosophically, this is important to solve, although it's possible that P equals NP in principle, but in fact, those easy solutions are very hard to find, and then cryptography would still be okay. That in principle, there's a backdoor, but we can't find it. Now, I see some comments in the chat here. Hello, everyone. Is a salesman problem like routers open shortest path first? Well, that's an interesting question. In principle, finding the shortest path through a grid of routers might be as complicated as the traveling salesman problem, but the OSPF protocol has a way of propagating a route without having to get stuck in some complicated list. So I guess in practice, it doesn't have to solve this difficult problem. I think because they just designed the protocol to do something simple by probably effectively a greedy search, I imagine. It's an interesting question. I wonder if I might be worth Googling for OSPF. In principle, you'd think the OSPF might be the traveling salesman problem for a complicated network. Yeah, the traveling salesman problem, but what about OSPF? Let's get OSPF in here. The algorithm is somewhat well studied. Well, anyway, I don't see an obvious answer here. It's an interesting question. In a complicated enough network, OSPF might possibly be effectively solving. If so, I'm sure it doesn't solve it perfectly. It makes some kind of approximate solution. Anyway, then of course there's quantum computers. In quantum computers, they've defined P and NP and a new categories out here of computers of BGP, all problems that quantum computers can efficiently solve, which they say will include some problems outside this area. So there's arguments about how quantum computing will change this. All right. Anyway, and here's the XKCD example of this. If you have a bunch of appetizers and you tell the server, I want $15.05 worth of appetizers, that is the knapsack problem. It is in fact not simple, even with such a short list, to figure out exactly what combination of these things will add up to that total. And that's the point. That's the hard problem. Anyway, so if breaking a cipher were NP complete, then it would be the strongest possible NP question. Seems like that would be best. But in fact, it turns out that those NP complete problems are not practical for cryptography, because although they tend to at large scale, they get very difficult, there are certain cases where they're very easy. And therefore, they have traps in them, like RSA does. There are problems with RSA. There are a bunch of particular kinds of prime numbers which, if you use them, they make RSA easy. It's the same kind of thing. So real cryptography does not use NP complete problems. It uses other ones, which are probably not even NP hard. So everything is sort of a practical approximation. Now, one other category is the lattice problems. This was Google's proposition to solve post-quantum encryption. And I actually was writing hands-on projects for New Hope when they broke it. So this was the only NP-hard problem ever successfully used in cryptography, was learning with errors, a lattice problem. Google actually made a cryptographic system based on this, and it was going to become the standard, but it was broken. And the current one, like Crystal Kyber, uses something else. So anyway, the factoring problem is the one you use for RSA. If you have a large number n that is the product of two primes, p and q, can you find p and q? This has been considered a difficult problem for thousands of years. And so prime numbers are all the numbers that cannot be divided by anything other than themselves and 1. So 1, 2, 3, 5, 7, and 11 are prime. 9 and 15 are not prime. So the simplest algorithm to find these would be to try dividing by all the numbers from 2 to n minus 1, and then you'll eventually find the factor. Now that will take, if n is the number of bits in the number, that'll take 2 to the n. You have to try all the numbers up to there. So that would be 2 to the 256 operations for a 256-bit number. So if this was the algorithm used to factor large numbers, then a 256-bit key would be fine for RSA. But there are more efficient algorithms. An improved algorithm would be to try only primes up to the square root. That turns out to be much faster. It's 2 to the n over 2 over n. which is much less than 2 to the n. So for 256-bit number, that only takes 2 to the 120 operations. And there is a thing called Eratosthenes sieve, where you take the prime number like 2, and then you cross off every even one. Take a prime number 3, cross off all the multiples of 3, and so on. So you filter it out. And there's a better version of it called the general number field sieve, and that can crack a 1024-bit n and only 2 to the 70 operations. So it's much faster. In 2048, it's 2 to the 90 operations. So since we want 128 bits of security, we now recommend 40,096-bit keys. So that even the fastest algorithm known would still take more time than we have to solve it. All right, and let me see, I think there's another comment in the chat. Nope, same one, all right. All right, good, just looked different on the other screen. All right, so here's experimental results. A 663-bit public key for RSA has been factored. It took 75 CPU years. And in 2009, a 768-bit was factored. So there's a general belief that the NSA can probably crack a 1024-bit RSA key because they have very fast computers and very good algorithms, and their cryptography is typically 10 to 20 years ahead of what's known publicly. So that's why, arguably, we shouldn't be using 1024-bit RSA keys anymore, and indeed, they're not recommended for any purpose anymore. Everybody thinks you should be using at least 2048, and you should be upgrading to 4096. So, is factoring NP complete? And that's the problem. We don't really know. No polynomial time algorithm is known, which suggests it's not NP, but we can easily verify a factor once it's found, so it's in NP. But we don't really know where it is in NP, and we don't really know that it's hard because we don't really know that anything in NP is hard. So we're using it under the belief that in current practice nobody can crack it, but we don't really know that it's going to stay that way. And here, for example, is the thing that's definitely causing everyone to move away from RSA, quantum computers. You make an arrangement of gates. You can carefully design an arrangement of quantum computing gates that will resolve a composite number into its prime factors with very few operations. However, the current generation of quantum computers are not remotely powerful enough to do it, so last I heard, the only calculation factoring that had actually been accomplished was 15, factoring 15 into 3 times 5. They can't get any bigger than that with the current generation of qubits that are noisy and the connections are not accurate and so on. But in principle, if they got like a million or a billion times better than they are, and you could have a big quantum computer, you could start cracking RSA keys. That's why people figure in maybe 20 years or 30 years or something that'll happen, and so we ought to start using a better encryption scheme than RSA, in case that ever happens. So here's the hardness assumption. All cryptography requires a problem which is assumed to be hard. And if you want to justify it, you can't prove how hard it is, but what you can do is prove it is as hard as some other hard problem. So, this is, like I say, the mathematics is a lot less hard, secure, and clear as you might think. You can prove that factoring and discrete logarithms, these are problems that have been famous and considered hard for centuries, and you can prove that whatever you're doing is as hard as factoring, and you take that out there. It's pretty good evidence that it's hard. So the discrete logarithm problem is a pretty obvious, simple generalization of the factoring problem. I think that's what I look at it. So here's the deal. You have to have a group, and a group is a set of elements and an operation that obeys certain axioms. So Z star P is a famous group where you have a prime number here, and that is the numbers from 1 to P minus 1. So Z star 5 contains 1, 2, 3, and 4. That's all it is, it's a group. Now you have, this is like the ring arithmetic we talked about. So here's the axioms. You have to have closure, associativity, identity, and inverses to have a group. Otherwise, you might have a set of numbers, but you don't have a group, a particular mathematical object. So closure means when you can combine two operations, you combine two elements with the operation, which we write as multiplication. It often is multiplication. So when you multiply any two elements of the group, the answer is still in the group. That's closure. You don't get outside the group. Associativity means you can change the order of operations. X times Y times Z is equal to X times Y times Z. And that's fine. So that's identity existence means for every element there is an identity, and if you multiply the identity times X, you get X. So this is 1, like 1 times X, and the inverse means there is an inverse, so that X times Y gives you the identity element. And that's what defines a thing to be a group. And it can be multiplication on a ring, which is what you use for RSA, but it can also be other, in principle, less obvious transformations that obey these properties. Now, there are commutative groups where x times y equals y times x. That is not required, but that is often the case. And there are cyclic groups, and these are ones where you can have a generator element, and if you raise it to powers, g to the 1, g to the 2, g to the 3, you will get all the group elements. So g is then called the generator of the group. And for RSA, you have a generator that hits most of them, although not all the elements. So here's the hard problem. The hard problem consists of finding y so that g to the y equals x. So you know the plain text, and you want to know what you'd have to raise the generator to create that plain text, and that's why they call it the discrete logarithm. It's basically the logarithm of x in this g space, mod to the base g. And this turns out to be a hard problem, about as hard as factoring. And there's varieties of, and we'll talk about them in later lectures, there are cryptography systems based on the discrete logarithm problem. It's quite similar to RSA, really, but it's a little bit more general. It's not particularly tied to integers and prime numbers. It's just tied to groups, of which integers and prime numbers are one possible example, but there are other examples. All right. So what can go wrong with this stuff? These are things that are possible, but people don't expect them to happen. For example, someone might find a fast algorithm to factor numbers. That would blow RSA out of the water. Someone could prove that p equals np. Both of those would be revolutionary, but both of those are things that no mathematician has been able to do for thousands of years, so people think they're probably not going to happen. Now, there is another problem I mentioned before. If you use prime numbers, if you choose the wrong prime numbers, then factoring gets easy. This 1024-bit number is easily factored because it's the product of not just two primes, but a lot of primes. And as you can see, some of them are small, so you can find some of these small primes right away, and that makes it easier to find the next ones. So certain numbers can be factored pretty easily. Also, if p and q are not random, this is what already happened on the internet a few times. The random number generators weren't good enough, so multiple devices would use the same prime numbers, and that's a problem. If they're near a known value, if you know some bits of them, or for example, of course, if n is too small, like 128-bit RSA or 512-bit RSA, it's just not big enough, you can't actually crack it with known algorithms. OpenSSL allows you to create short keys. It's not wise, but you can do it. So here's the original RSA paper from 1978, and in 1978 they said that a 500-bit key, which is 200 digits, would be fine because that would take 1 billion years to crack, based on computers from 1978. The problem is computers kept getting better with Moore's law, so that's no longer good enough. And that's the other problem with all cryptography, is you have to consider that computers will keep getting better and plan for the future. All right, and here's other ones that happened. Logjam, because the U.S. government wanted to block export of strong cryptography to other nations, they created weak cryptographic systems and built them into Windows and other devices for export. And so now they poisoned the internet with a bunch of servers and clients that can only speak weak cryptography. So the logjam attack will intercept HTTPS requests and alter them so they tell the server that you are an old computer, can only speak one of those weak cryptographic systems. So they downgrade the cryptography to 512-bit keys that can be cracked. And another one here, there's millions of servers that in fact use the same 1024-bit secret prime number, and it appears, and if someone could figure out that number, they could break in, and there is evidence that the NSA does have knowledge of that number. So certain systems do in fact use a certain recommended number, and if you use that, it's possible the NSA can get in. There's a link explaining more details with that one. And this is the logjam attack showing, when this came out, I think was 2015, they showed that an enormous, here's how many servers are vulnerable to logjam, and it's a lot. Like 14% of the IPv4 address space, and logjam apparently also, there's this common 1024-bit group that's broken, and in that case, it would be like 25% or more of the servers on the internet were vulnerable at that time. So this is the problem. With cryptography in practice, doesn't live up to even the best of the mathematical possibilities. All right, let's try Kahoot. I should have them here. All right. This This one. Oh, a lot of people. Good. I'll wait a bit more to see if more people are coming. All right. All right, so which complexity class is the hardest? Yep, exponential, 2 to the n. All right. All right, which problems are the easiest? That's it. P are the easy problems that can be solved in polynomial time. NP are all the hard problems. All right. Or at least NP are most of the hard problems. There are some other problems that are not even an NP, like impossible. Anyway. All right. All right. Which one is what's the knapsack problem? What type is it? NP complete. Those are the hardest NP problems, which have never been used for cryptography except just once by Google, and it didn't work. Anyway. All right, how about factoring? What kind of problem is that? It's just NP. It's not NP hard. Now let me go back to the slides because I can't remember what NP hard is. See if I can get it right. I have trouble remembering this stuff. It's a little abstract and vague. Okay, NP hard. The NP complete are the really hard ones, like the knapsack problems. NP hard are even harder than NP complete, apparently. All right, so maybe NP complete shouldn't be considered the hardest problem. Well, that's why I'm a little confused. The hardest problem is in the class NP, but NP hard might be even harder. So some of these statements aren't quite right, I think. All right, the NP hard are ones that are thought to be the hardest. And perhaps even harder. Provably as difficult as NP complete, but maybe even harder, and may not even be an NP. Okay, so that's kind of weird. The NP hard group is pretty weird to understand. All right, anyway. All right, let's go back to the Cahoots. No wonder I can't remember what NP hard is. That definition doesn't make much sense. Probably have to really read a research paper to get a better idea what it's about. Anyway, all right. How long should an RSA key be for enough security, which is 128 bits? That's practical information we should know, even if you can't keep all that abstract theory. Okay, 4096 is what we should be using, or perhaps the 3000. That's what we should be using these days. 1024 is not enough at all. That hasn't been enough for about 10 years. And even 2048 is no longer considered enough. We should all be moving up to 4096 bits. All right. Right, so it's lurker. Richie, if you want points, you have to make sure my grader can tell who you are. So I don't think we know who little lurker is. All right. Anyway, I'll stop this video.